And we're on. Okay.
So did y'all notice that I posted the first assignment to next week? So 4 problems. Let's see. So the problem with meeting on Tuesdays and Thursdays is it gets to Tuesday. I'm like, where were we? But anyway, let's see. So we just got to the point where we said the perihelion distance is a times 1 minus e, and the aphelion distance r, so today is a times 1 plus e. And now we talk about gravitation, since that's kind of what we're all about in this chapter. So, but before we begin, what questions might you have? Nothing. Okay, let's get started then. So, gravitation. All right, so we'll establish our symbols here. We've got 2 objects gravitating, because that's super important, obviously, in astrophysics, right? Binary stars and whatnot. So there's 2 objects, masses M1 and M2. And I'll draw a dashed line, the line joining the 2 of them. And the gravitational forces will be equal and opposite. Gravity obeys Newton's 3rd law, certainly. So they have equal and opposite forces they exert on one another. And we're going to say that F sub 1, 2, in that order, is the force on M1 due to M2. That would be our convention. It's on the first subscript by the second subscript, so to speak. So that's force on M1 due to M2. And so notice, I've got it pointing towards M2 because they're attracting one another gravitationally. And so then we draw an equal and opposite arrow, so to speak, to represent the force exerted by 1 on 2. So that'll be F21 and F21, and F12 are equal and opposite. So F12 is minus F21. And we also will note some unit vectors. So in other words, there will be r hat 1, 2, which points from 1 to 2. And there will be r hat 2, 1, which points from 2 to 1. And so they should really be drawn on top of the masses, but I shifted them a little parallel because I don't want to confuse it with the arrows that represent the forces there. And so R12, which of course you could also say R21, is the distance from M1 to M2. And R hat 1, 2 is unit vector from M1 to M2. And that'll be equal to R2 minus R1 divided by R12. Right? Because I remember the way vectors work. If that is A as a vector and that is B as a vector, then if I go like that, that arrow right there is B minus A, because if I added them up, right, it would be A plus B minus A would be equal to B. So remember, keep it in your head, if you have a subtraction of 2 vectors, then that points from the back end to the front end, so to speak. In other words, B minus A points from the tip of A to the tip of B. You can write that down. Right? Burn that into your brain. You know, you derive it. A minus B would point the other direction. And so if we do our R2 minus R1 here, right, if I've got these two masses, and I had some origin over here somewhere, then there would be R1, the position vector of mass 1. There would be R2, the position vector of mass 2. And so if I want R12 there, well, here, what vector is that right there? So R1 points to M1, R2 points to M2. What is this vector right here? This is the vector R2 minus R1, right? This is R2 minus R1. And any vector divided by its magnitude is a unit vector in that same direction. And that's why R hat 1, 2 is R2 minus R1. It points from 1 to 2, divided by its length. That's how far away they are from one another. That's the length of that vector. That's why this is that unit vector. Are you buying what I'm selling? What questions do you have? Or comments? Or observations? You look like you're...
I thought I did, but I realized this is just a different format for something I see before. So
Oh, okay. All right.
I might have a question.
Feel free to have one later. Yes, for sure. At any point. Okay. Right, and so R21 is minus R21 hat is minus R12 hat, so it would be R1 minus R2 over R12, right? Might as well just go ahead and read that. Over R12, and either, I could put R12 or R21, those are the same thing. And let's see, right, so I'll just point out that R1 and R2 are the position vectors of M1 and M2 with respect to whatever origin we've picked. Right, remember, the position vector of a particle is the vector that connects the origin to that particle. You get to say where the origin is. But note that while R1 and R2 depend on where I put my origin, their difference does not. That's always pointing between the two masses. Just getting your brain back in gear for all these sorts of things here. And if we want to write Newton's law of gravity, is this stuff erasable yet? Can I erase this stuff? Speak now or forever. Ah! Okay, it's gone. Well, it's not gone, it's still on that, but whatever. Okay, so Newton's law of gravity says that F12 is equal to G M1 M2 over R12 squared times R hat 1, 2, the force on 1 due to 2, due to the force M1, the force on M1 due to M2 is of magnitude Gm1 M2 over R12 squared, and it's in the direction from 1 to 2. Anybody know? What do we call capital G there? That is the
Gravitational constant.
Yeah, the gravitational constant, the universal constant of gravity, whatever you want to call it, the gravitation constant, not to be confused with little g, which is just the acceleration due to gravity on whatever planet you're on or whatever. That's a little pet peeve of mine when people say, gravity is 9.8. Stop it! That's the acceleration due to gravity at Earth's surface, that's not gravity! Sorry, I got a little carried away there. The gravitation constant if I remember what it's equal to, it's actually not that hard to remember. What? You don't remember the gravitation constant? 6.67 times 10 to the minus 11th power Newton meter squared per kilogram squared. That has to be the units, right? Because M1, M2, what's the units of M1, M2? Each one in SI, each one is, no, we don't. This is exciting stuff. M1 and M2 in SI units would be expressed in kilograms. So M1, M2 is kilograms squared. So G better cancel those units. And then R1, 2 squared is 1 over meter squared. It's their denominator. These meter squareds cancel that, leaving just newtons, which is the force. And so, yeah. Of course, if you want, you can express this entirely in terms of meters, kilograms, and seconds, but it's more convenient often to just think of it like this because you want the force to be in newtons. So, you know, remember that a newton is a kilogram meter per second squared, so you could throw that in there too and turn it all into meters and kilograms and seconds. But in any case, that's easy enough to remember, I feel, because it's just about 2/3 times 10 to the minus 10. Right? 6.67, 2/3 times 10 to the minus 10. And so, you know, I'm not going to require you to memorize that, but just memorize it, it's easy. And then F21 is G M1, M2 over R21 squared R21 hat, but that's just minus F12 because R12 hat and R21 had an equal on opposite unit vectors. So like any self-respecting force in classical physics, it obeys Newton's third law. That the gravitational forces that the two bodies exert on one another are equal and opposite. Now, there's a bit of a problem here, which we're not going to worry about at all for now, which is, notice that it seems to be saying that the force depends on the instantaneous positions of the two particles. Well, suppose that these two particles were, say, 1 light hour apart, and I moved one of them. The formula would say that the force on the other one follows around the motion of the other one. But if they were, say, 1 light hour apart, and I moved one of them, could the other one know that it had been moved yet? And if not, why not? The answer is no, it couldn't know that. Why not? This is something that bothered Newton because it seems to be saying that there's action at a distance and that the two particles can somehow know instantaneously where the other one is. Mac, you seem to be...
Wouldn't it have to, something would have to go faster than light?
Yes, yes. If it could instantaneously tell where the other one was, that information would have reached it faster than light. If they're a light hour apart, the quickest one could find out about any changes in the location of the other is an hour later. And in fact, what really happens is if you move it, a gravitational wave moves at the speed of light and carries that information between them. But in classical Newtonian physics, gravity travels at infinite speed, in a sense. In other words, they're instantaneously able to know where one another are. And often it's fine to ignore the fact that really this would violate relativity. That's just kind of an aside. But it just occurred to me to say, I wasn't even going to mention it, but then I had to. So, all right. Let's see. I think I'll leave that up there for now. What questions do you have? Okay, can I erase all this stuff? Let's talk about gravitational potential energy, and I'll remind you of how all that works. I'll remind you of the work energy theorem. You probably, did Dr. Trees derive the work energy theorem for you in 110 or whatever? Or do you remember what the work energy theorem says?
Sounds familiar.
If you find the work done on a particle between 2 points, the total work done on the particle, that's equal to the change in the particles. What's that? What kind of energy? Kinetic, yes. Yeah. Work equals change in kinetic energy. Good thing we're reviewing all of this to get it back into your head. All right, so gravitational potential energy. What we're going to see is you define the potential energy to be minus the work done on the particle, and then as long as that's independent of path, doesn't matter how the particle got between the 2 points, the whole point is that if you define the change in the potential energy to be minus the work done, well, by the work energy theorem, the work done is equal to the change in the kinetic energy, so it's automatically true that the change in the kinetic energy is equal to minus the change in the potential energy, and therefore that the total energy is conserved. That's the whole point of defining potential energy the way that we do. Well, let's go ahead and define it that way so that you can see it for yourself in action. So gravitational potential energy. Gravitational potential energy. All right. Let's have a mass that we'll call capital M sitting at the origin. And let's go ahead and say there's a XYZ Cartesian coordinate system there, although we're not going to particularly make use of that right now. But just think of it as sitting at the origin of our coordinates. And so here is the initial position vector r sub 1 of some cute little mass, wow, my voice is a little weird today, little mass m that is moving in the gravitational field of big mass capital M in between points 1 and 2. So in other words, little m starts at position vector r1, ends at position vector r2. It follows this dotted path, let's say. And so we could talk about a little dr, a little displacement of mass little m along that path. And so the position vector of m itself, little m itself, if I wanted, I could draw another arrow and just call that r as a function of time, the position vector of mass little m. But in the interest of not overly cluttering my diagram, if I were to draw the gravitational force on little m, what direction does it point?
Plus y.
Not plus y, because what's putting that force on little m? So the gravitational force on little m is due to,
Z.
now, so don't be confused by this little displacement right there. That's just the motion of the particle. It's moved a little bit. But there's a gravitational force on little m due to what's pulling up big M. So the force on little m points towards big M. It's a gravitational force towards big M. So I'll draw an arrow here and label that F. That's that gravitational force on big M, little m I meant, pointing towards big M. And we'll assume that big M is bigger enough that it hardly moves under the influence of little m, or that we've got magical space-time nails that have locked big M into place at the origin, like that. So big F there is gravitational force on cute little m due to big M. The work done by a force F acting through a displacement dr doesn't have to be this force, it can be any force. I've got a force F acting through a displacement dr, little dr. Cute little dr is dw equals what? Don't make me tell Dr. Trees on y'all. dw is what? Well, it's a little bit of work. So we don't even have to think of it as a difference. It's just a little bit of work. And physically speaking, if you apply a force F through a displacement dr, there's a vector formula that gives us the work. So, gosh, is it a cross product? Is it a dot product? Is it, what is it? Yes?
Is it a cross product? You said dot product.
It's, I figure, it must be the other one, right? It's a dot product, because work is a scalar. Cross product, remember, is a vector. Work is a scalar, it's just a number, okay? So it's what? It's a dot product of, I've handed you all the ingredients here. F dot dr, yes, F dot dr. So dw is F dot dr, right? So Franklin Delano Roosevelt, right? FDR, except it's the dot product there. Every time I say that, I think of FDR, oh, Franklin Delano Roosevelt. F dot dr, okay? That's, by definition, I can make that the triple equals of definition. That's the definition of the work done. Of course, we only care about making that definition if there's something useful that comes out of it, and that is, in fact, the work energy theorem, as we'll see. Now, actually, to get our particle to move along this silly trajectory right there, I'd have to be applying some other force on it to force it to move that way. So this would be the gravitational work done on it, and then I was also doing some other work on it with my force that I was applying to it, and we're just interested in the gravitational work done. So, the total work done on the particle as it travels from, actually, so, sorry, I'm going to change my subscripts here. I'm a terrible person. R sub I, R sub F, initial and final. I could call them R1 and R2. Let's call them initial and final. And yeah, if you're on a tablet, if you're not, you're cursing my name right now. I had to erase what I wrote. Okay, total work done. On the particle as it travels from Ri to Rf is, well, dw is f dot dr, so if I want to find out what w is, 2, 4, 6, 8,
That's integrate.
yes, or something like that, let's see, 2, 4, 6, 8, now it's time to integrate, let's make it like that.
I thought it was wrong.
No, it is to integrate, that's right, yes. Sometimes it's 2, 4, 6, 8, time to differentiate, that's already the differential, so
Yes.
gotta stand on our head. 2, 4, 6, 8. Now it's time to integrate. Yes. Okay, so that'll be going to add up all the DWs, right? This will work, this will work, this will work, this will work. Of course, there's an infinity of them to add up, right? It's the usual calculus. You break the path into an infinite number of infinitely small displacements and calculus, right? So we integrate. You could represent it as a finite sum that goes over to the integral, blah, 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 blah. Add up all the little DWs, or in other words, we go from our initial to our final of f dot dr. So we add up f dot dr for all the little drs along the path. But Newton's second law says that the force on the particle, if it were the only force acting, would be what? F equals MA. I'm just looking for F equals MA. F equals MA. What's another, what's the acceleration? It's the derivative of what vector? Velocity. So that's m dv dt. So let's use that over here. So we're adding up from the initial time to the final time. The time, okay, so we're going to change this from an integral over dr to an integral over time by saying, okay, it'll be a time integral from its initial time to its final time when it was at those two positions of the force is m dv dt dot v dt, right? Because v is equal to dr dt, right? It's the derivative of the position vector with respect to time. So dr is v dt, so this is force dot dr. ma dot v dt is force dot dr. Find what I'm selling? Questions what questions do you have at this point? Okay, so let's get all fancy here. So we can pull m out of the integral because that's just a constant. M integral from ti to tf of ddt of 1/2 v dot v dt. Now why do I say that? Well, if I take ddt of v dot v, dot products obey the product rule, right? So if I have two functions, ddt of fg, what's the product rule? Calculus, what's the product rule say? That derivative is equal to. It's just two functions of time, f of t and g of t. The derivative of the product is, how do you do that? Yeah, the derivative of the first times the second, plus the first times the derivative of the second, right? So this would be df dt g plus f dg dt. And that applies to the dot product too. If I had ddt of a dot b, where it's understood that this is a as a function of time and b as a function of time, then this would be equal to dA dt dot b plus a dot dv dt, we get to use the product rule of derivatives for dot products. And so ddt of v dot v is, how can I break that apart? If I just apply this rule right here, where A and B are both V, what do I do here? This will be dot plus dot wherever is a syllable, fill it in, so we get dot
dv dt dot v
right?
plus v dot dv dt.
Yeah, dv dt dot v plus v dot dv dt. Now, are dot products reversible? Is A dot B equal to B dot A?
No.
Yes.
Yes, yes, they are. If you just think of it in terms of either it's the product of the magnitudes times the cosine of the angle between them, or product of the magnitudes, doesn't matter which order you put them in, the angle between them doesn't depend on what order you put them in, or do it in terms of components, right? Ax bx plus ay by plus az bz, wouldn't care whether you reverse the ax and the bx and so on and so forth. Cross products, that matters. If you reverse the order of a cross product, it flips the sign, but not a dot product. So these are both the same thing, so that's the same thing as 2 v dot dv dt. ddt of v dot d, of v is 2v dot dv dt. And so in other words, if I take the derivative of half v dot v, it's dv dt dot v. That's how I'm going from here to here. The derivative of half v dot v is dv dt dot v. Because when you apply the product rule, you get dv dt dot v plus v dot dv dt, which would be 2 dv dt dot v times a half is dv dt dot v. So I can do this, right? Happy? Not happy? So, meanwhile, if I take any vector and dot it with itself, so just generically, A dot A, what's that equal to? How would you describe what that's equal to?
A squared.
A squared. A squared is just equal to A squared, which is what we mean by, in other words, the magnitude of A squared, which we often just simplify by the A squared. A squared, like that's understood to be the magnitude of the vector A squared, right? Because A dot A is going to be the magnitude of A times the magnitude of A times the cosine of the angle between A and A. What's the cosine of the angle between A and A? Well, what's the angle between A and A?
0.
And what's the cosine of 0? 1. So the dot product of any vector with itself is the square of its magnitude. That should be just totally burned into your brain. So if it's not already, light that flame, brand your brain, such that if they did an MRI, they would see that on the surface of your brain, okay? Actually, don't do that. That would probably be cause for some surgery or something. But anyway, figuratively burn it into your brain. So this is equal to, in other words, what am I going to say? M times the integral from Ti to Tf of d of 1/2 v squared. No, I don't want to do that. I want to say vi. Well, I'm going to erase that and just write it again. It's getting too much clutter there. So, what I'm saying is my next step would be, I'm going to say it's equal to, now I'm going to change it from a t integral to a v integral because d dt of something dt is d of that something. So in other words, this whole thing here is the differential of the quantity 1/2 v squared, because in what my very first calculus professor called an example of bad algebra but good calculus, why, we can cancel the dt's, so to speak. Okay, that's fishy, but it turns out it's legit. So this is the differential of 1/2 v squared. And so we're going from the initial velocity to the final velocity equals m initial velocity to final velocity of the differential of 1/2 v squared. And the integral of d something is something, right? If you take the integral of d something, it's something. The integral of dx is x. The integral of d schnorkenhock is schnorkenhock, or whatever. So this is equal to m times v squared evaluated between vi and vf times a half. It's equal to half mv squared, because there's a half over there, half mv squared evaluated between vi and vf. What that? What's this symbol mean? It's, yeah, that's right. So it's going to be 1/2 of mv final squared. I'll just pull the half m through, minus 1/2 of m the initial squared, right? Because this always means put in the upper limit, subtract, put in the lower limit, and subtract. So this is 1/2 mv final squared minus 1/2 mv initial squared. But what do we call 1/2 mv final squared? Or what do we call 1/2 mv squared in general? Why, that's the particle's kinetic energy, right? So this is the final kinetic energy. That's the initial kinetic energy. In other words, this is equal to delta K, the change in the particle's kinetic energy, which was the whole point of this exercise, right? In other words, we just proved the work energy theorem, that the total work done. Notice I did not use the fact that this was supposed to be a gravitational force. It's just generically a force. We never used any specific mathematical form for it. And we showed that if you add up the work done by that force and use Newton's second law, that force is mass times acceleration, it automatically becomes that the work that you do is equal to the change in the kinetic energy. So this is the glorious work energy theorem. Parentheses. And there was much, what's the next word? And there was much rejoicing, yes. And there was much rejoicing. All right, rejoice with me. 1, 2, 3, hey! Woohoo! All right. Okay? Glorious. Actually, I will say, you know what, so back when I was in college, I took freshman physics and certainly did lots of, energy conservation problems and stuff like that. It was around about when I was a sophomore that soaked in. That, oh, it's a concept, so if you're like, I was today years old when I really, or whatever, that's fine, right? If you never understood it before, and if you're still hazy on it, soak it in, and that's where that's coming from. That's the proof of the work energy theory. Sometimes, I'm sure they must have proved it in class, or maybe they said read it in the book or whatever, but things don't always soak in the first time you see it, because you're like, I gotta learn how to use this, So, that's where it comes from. Worth having that through your head. worth getting to the point, I don't think I'm gonna quiz you on this, but worth getting to the point where you just do this, you know, just from scratch, basically. I could, like, yeah, you're a prof, but anyway. I've been doing this for years. So the work done is the change in the particle's kinetic energy. So how are we going to get energy conservation? By defining the change in the potential energy to be minus the work done, so that the change in the potential energy, delta U, is automatically minus delta K, so that E equals U plus K stays constant. That's how you define potential energy. To get energy conservation, you define the change in the potential energy to be minus the work done. And you already knew that the change in the kinetic energy is the work done, so blah, blah, blah. In order to obtain conservation of energy, I'll say conservation of total energy, E equals K plus U, where of course that's the potential energy. We define the change in the potential energy to be minus the work done on the particle. So we say U final minus U initial, delta U equals U final minus U initial is equal to minus the integral from the particle's initial position to its final position of F dot dr. But the somewhat subtle point here is we can only get this to work if it doesn't matter how the particle got between R1 and R2, Ri and R final. It has to be true that no matter what path the particle took, this integral would always give the same thing, so that the change in the potential energy only cares about where the particle started and ended, and not how it got between those points. That way, this will be a well-defined function of the particle's position. By well-defined, I mean single value. For this to be a well-defined function of the particle's position, the integral must not depend on the path the particle takes between Ri and Rf. Must not depend on the path the particle takes. Because if it did, one path would give one value for delta U, another path would give a different value for delta U. Well, then which one do you pick? None of them would be any better than the other. So for this to work, for this to give us energy conservation, it has to not matter how the particle gets from the start point to the end point. It must not depend on the path the particle takes to get from Ri to Rf. In other words, the force F must be, what do we say? What's the word for that? What kind of force is that? Hint. We're talking about conservation of energy. So the force has to be conservative. We say that it's conservative. The force has to be conservative. The force must be conservative. It has nothing to do with its politics. It's all about whether it cares about path in terms of the work that it does. So if the force is conservative, we get conservation of energy. What questions do you have? So now we need to show that gravity is a conservative force, that the work actually is independent of path. So that's our next challenge. And of course, the answer is going to be yes, right? And I will be like, oh crap, it's not conservative. I wasn't even doing this, right? But the other thing to note is gravity is an inverse square law of force. It goes like 1 over distance squared. What's another inverse square law of force of your acquaintance? Which is studied in Physics 111. That was an inverse square law of force. Yeah, in electricity. Coulomb's law also goes like 1 over the distance squared between the particles. And it's on the line joining the particles. And so, if we prove that gravity is conservative, we also prove that the electrical force, the electrostatic force, is also conservative. That means you can define potential energy. That means you can talk about the electric potential and all that kind of goodness. It's the same math. It's exactly the same math. So, let's show that the gravitational force is in fact conservative. And it's funny, because it turns out that one thing that a school like us sometimes have problems with is some parents misunderstand that when you say you're a liberal arts institution, it doesn't mean you're politically liberal necessarily, right? The liberal arts have nothing to do with politics. Not everybody knows this. And so sometimes the admission has to explain to people this has nothing to do with anybody's politics. Liberal as in liberating, not, anyway. So, okay, well actually let's take a break here because I would end up drawing a pair of circles and then just going back to them if you need. So we'll take a break here. And you'll just enjoy the exciting conclusion of the video. Stay tuned.
See you on Thursday.
Yep. All right, so now, remembering that I'm not Dr. Trees, I'm going to draw 2 concentric circles and then locate their center. Note the order in which I said that. Circle number 1. Circle number 2. So much pressure.
You can do this.
I can do this. We So here we have big M at the center being a source of gravity. And here we have cute little m, and it's moving somehow. It got thrown, it's moving, it's got some KE, so it doesn't necessarily just fall straight in towards m. So let's say it makes a little vector displacement like that, dr, taking it from radius r away from big M to radius r plus dr. So in other words, dr is the difference in the radii of those two circles. So there's radius r, here's radius r plus dr. So notice that little m starts a distance r from big M, ends a distance r plus dr from big M, taking a slanted path to get there. And so, just for kicks, what if the force, do I really want to do this? Yeah, I do. So, let's say the force were actually an outward force. It's not, it's inwards in this case, but just for sake of argument, what if those were two positive charges? Then the force would actually point outwards. And it's going to end up, the force is conservative just because it's central, just because it points towards the center of attraction here. So let's, just to keep that algebra slightly simpler in a minute, let's say F were radiated outwards. We're pretending this isn't actually gravity in this case. So let's say that theta is the angle between F and dr, between the force F and the displacement dr, because theta would show up in that dot product, right? It would be the magnitude of F times the magnitude of r, dr times the cosine of that angle theta right there. So W, which is F dot dr, is equal to the magnitude of F times the magnitude of dr times the cosine of that angle theta between them. And we'll note that if that force on the particle is an outward radial force, radial just means towards or away from the force center, the thing that's exerting the force. So it's either pointing straight inwards or straight outwards from the exerter of the force. It's an outward radial force, if that were the case, then that displacement dr's magnitude times cosine of theta is equal to little dr without an arrow on it. In other words, this notation is admittedly a little sloppy, but it's what we do. D little r with no arrow on it is simply the change in the distance from the origin. It's just the distance between the difference in the radii of those two circles right there. And see, notice then that I can make a little right triangle here, and of course there's going to be one of these in the limit as the magnitude goes to 0, but we've got essentially what looks like a right triangle where dr, the magnitude of dr is the hypotenuse, and the angle from the radial outward direction is theta, and so how much you moved outward here is dr plus theta, that leg of the triangle, the leg adjacent to theta. Is that making sense or not? You're just kind of staring at me. Is it making sense or not? So you're okay, I'll leave you. Okay, because it's important to be happy with this. Right? So that's little dr there, right there, right? Without an arrow on it. So magnitude of dr, the length of that dr displacement, cosine theta is the adjacent side, just a little dr right there. And again, strictly speaking, this isn't the limit as everything shrinks down to zero size. There's a little bit of approximation here from the fact that I've drawn an actual finite difference in radii between those circles. So if F is an outer radial force, then the magnitude of the displacement cosine theta is equal to d little r, the change in the distance from the origin, which is the change in the distance from the origin. Change in the particle's distance from the origin. Change in the particle's distance from the origin. Whether or not, if you really think about it here, whether or not that change is positive or negative, because if the particle had moved closer in, if I were like this, and the particle, so this is a hypothetical over here, if it would make that little displacement dr, then F would point like this. Theta would be more than 90 degrees. What would be true about cos theta if theta is more than 90 degrees? Would it be positive or negative? Yeah, right? So 90 degrees, or pi over 2 if you like, right? Theta, cos theta. Always think of the plot when you're trying to answer questions like that, right? So it's 0 at 90 degrees, it's positive between 0 and 90, negative between 90 and 270 really, right? So in other words, if it moved inwards, cosine theta would pick up a minus sign, and that would make that would make the dr cosine theta be negative in that case, and so dr would be negative in that case, and so it'd still be true that this held, and the cosine theta would indicate the fact that this quantity was less than 0, that it had gotten closer to the origin instead of further away. So that's why I say whether or not dr is positive or negative, dr cosine theta is equal to its value, no matter what. Because if it's moving outwards, cosine theta will be positive, and if it's moving inwards, cosine theta will be negative. So we're good to go there. In which case, then, we can say that f dot dr is just equal to f dr, where by f I mean the magnitude of f, but dr is not the magnitude of the little displacement dr, but instead the change in distance from the origin. So you got to be a little careful about what things mean. And I'm hoping this is the kind of thing that it can be made to sound complicated when it isn't. So I'm not, just being very careful here, but it's not complicated. It's one of those things you have to know from the context that while this, the symbol f means the magnitude of f, the symbol dr is not the magnitude of the vector dr, it's the change in the distance from the origin. One could make a case that maybe we should call the displacement s instead, but then you'd still be getting to like s versus r and so forth. The point here is that notice all that matters is how much its distance changed from the origin, not the path it went to make that change. In other words, it wouldn't matter if it went straight outwards or at some angle theta. All that matters is how much further it got from the origin, not the direction it was moving to get that extra distance from the origin. And this is going to mean that the force is conservative. This is going to mean that the force is conservative. So now, in an effort to make this as confusing as possible, it's not actually an effort to make it as confusing as possible. I'm just saying that facetiously, but in other words, I'm just being careful. I just want to be careful, but it means I'm saying extra words which might make it sound complicated, but it's not really. Trust me. For an inward radial force, what would be an example of an inward radial force that we might want to study? Yes, gravity, right? Yes, like gravity. Like gravity. The magnitude of dr times cosine theta is equal to minus dr, which doesn't mean it's necessarily negative, right? In other words, this quantity is not necessarily negative because if dr is negative, minus dr is positive. So it's algebraically the opposite sign from whatever dr itself is. It's minus dr. Since then, theta is equal to 180 degrees minus the angle between dr and the outward direction. So that f dot dr is equal to minus f dr instead of f dr. If you like, just think of the fact that, well, if f is inwards, it has to change the sign compared to what it was before. Because now the angle is 180 minus what it would have been before. Right? In other words, if I now say there's an inwards force, then that would be the new angle, which would be 180 degrees minus the old angle, but the cosine of 180 minus theta is minus the cosine of theta. So this is coming from that idea. Again, this sounds way more complicated than it really is, and if you're kind of like would, so you might be going like, yeah, whatever, but if you're going like would, stare at it carefully until you're convinced that you've got this down. Basically, for outward forces, outward radial forces, F dot dr is F dr, and for inward forces, F dot dr is minus F dr. So it depends on whether Franklin is positive or negative in this case. Good old Franklin. What questions do you have?
That was very good grade.
Oh, good. I'm glad that you're very good. Yes. Okay. So, what questions does anybody have? Shall we continue? Please just keep going down here. Okay. So, thus, for gravity, we have that UF minus UI, i.e. the change in the potential energy, will be minus the integral from Ri to Rf of F dot dr. Right, in other words, minus the work done. So in other words, this minus sign isn't here because of this. This is just always going to be true when we're defining the potential energy. i.e. delta U equals minus work done. So this minus sign would always be there, but now it's going to kiss this one, and they'll annihilate one another. So this will be plus, because of the fact that this is minus FDR. Right, so this is going to be minus minus FDR, so we get plus the integral from Ri to Rf of FDR, and notice I took the arrows off because of the fact that now we're just interested in how far we started, how far we ended. Because all we're adding up is changes in the distance from the origin. However you might be effecting those changes, causing them to come about. So now we put in, okay, well what is that F? What's the magnitude of F? Integral from Ri to Rf of, well what is the magnitude of F? What's Newton's law of gravity? It's G times, this time they're not all syllable, we just need one. But now I'll make it. So here we got mass big M, mass little m, so it's going to be G,
The little m times big M over the distance between them squared.
yes, well, R squared, yes, you're correct, right? But in terms of my syllabi,
Squared.
right, they did not go, right, I just went,
My fault.
no, I'm just crazy. Okay, plus G big M little m over R squared dr. So just not the distance between them squared, which well it is, but said more compactly, just over R squared, right? Okay. Oh, but wait a minute. I'm guessing you know what the integral of 1 over R squared is generically. What's the integral of 1 over R squared? What's the antiderivative of 1 over R squared? Because we're just integrating with respect to R here. Well, that's right, it's R to the minus 2, so when I integrate R to the minus 2 dr, what's the rule? What do you do to the exponent? When you integrate, you add what to it? You add 1 to it, and then you divide, right? So this would be minus R to the minus 1, right? Minus R to the minus 1, also known in certain circles as minus 1 over R. So that's what we'll call it here. So this, carefully avoid the circle. This is equal to minus G big M little m times 1 over R, evaluated between Ri and R final. Or in other words, it's minus G times 1 over Rf minus 1 over Ri. Is the change in the potential energy. Change in the potential energy is minus G big M little m times 1 over Rf minus 1 over Ri. Now, potential energy, all we care about is changes. So remember this bit about, well, you can choose your reference point, which amounts to, you can add an arbitrary constant everywhere to the potential energy, and that won't change the change in the potential energy if you have the same constant everywhere. In other words, because only changes in potential energy are physically meaningful, we are free to pick where we want U to be 0. Right, remember that? Change only changes, right? So, because only changes, in PE are physically meaningful, not the value of the PE itself. I mean, physical education is very valuable, but that's what I'm talking about here. Are physically meaningful, we are free to choose where u is equal to 0. And given that 1 over r business there, a natural choice is let u be 0 where r is infinitely far away in that limit. If we let ui goes to 0 as ri goes to, well, I just say, if we let u go to 0 as ri approaches infinity and drop the f subscript, we just say, well, that's just where we are. You can imagine, well, what if the particle started out infinitely far away and then finally ended up wherever it is right now? You did that before, like with E and M, right, where you define the electric potential energy 0 at infinity, and then it just becomes k q1, q2 over r when it's the distance r between the particles. We're doing that sort of thing here. If we let u go to 0 as ri goes to infinity and drop the f subscript, because if we want that around, then we can write that u as a function of r for little m in the field of big M is minus g big M little m over r. And that's so important it gets a box right there. So that's what we usually do. We say potential energy 0 to infinity, in which case anywhere else it's minus gmm over r. So notice, as r decreases, what's happening to u? As r gets smaller and smaller, u gets what in magnitude?
Larger?
It gets bigger in magnitude, but also it's really becoming more and more negative, right? And a bigger negative number is smaller, right? In other words, right, a bigger negative number is smaller than a smaller negative number, and you know what I mean. So if you have a particle far away and it's just moving along, its gravitational, and it's getting closer to the force center, its gravitational potential energy is therefore, is it increasing or decreasing as it gets closer to big M? It's becoming more negative, so therefore it is decreasing, because we're talking about truly the value, right? So in other words, the number's becoming more negative, so it's decreasing. Minus a million is less than minus 6, for example, right? So it's decreasing. U is decreasing. Well, what's the kinetic energy doing? Increasing by the same amount, because the total energy stays constant, because we constructed it to do that, right? The change in the potential energy was constructed to be minus the change in the kinetic energy. And so as U decreases, K increases. This is not surprising. In other words, if you fall towards something, you're going faster and faster as you go. And that's what this is saying, right? So the total energy then is then E equals K plus U, or in other words, we'll say E equals, for little m there, 1/2 mv squared minus G big M little m over R. So for our two objects, big M, little m, and all we care about, we're assuming big M is so big that really we're just worried about what little m is doing. we're assuming that big M isn't moving much under the influence of little m, then if all we care about is little m, we would say that its total energy is its kinetic energy half mv squared minus its potential energy g big M little m over r, which we really understand that's actually the potential energy of the system of two particles, but that's fine. Put another way, if we assume big M is just sitting there, it's not putting any kinetic energy in it, so we just say that. Okay? Happy, unhappy, questions, comments, observations? Glorious. Why, let's talk then about escape speed and orbital energy. And can I erase this applause word from the thing? I mean, it's kind of, I'm going to do it. I can't hold it out. It's just, But yeah, it's on the card, so I can go back to it whenever I want. Now I have to arrange for this to happen too. Like a couple of years ago, I was recording a class like this, and I drew a dash line. You know, on YouTube, you can play videos back at high speed without, and it digitally processes it so that your voice still sounds the same. I was a woodpecker. It was great. I mean, I'm like drawing these dash lines, like, it was magnificent. I can't even imitate it as I go. You know, if you imagine it, was great. Why, even this time, if for no reason, I just went. And somebody just happened to play it back at high speed. It might be amazing what it sounds like when you do that at high speed. I'm just saying.
You gotta do the thing where you can just drag it into those dots. I've seen people do that.
What's that?
There's some people can do where they just drag it across. They
Oh,
hold
and it
it.
goes
Yeah,
next
I
to
can't
dash
do it.
line. I'll bet Dr. Trees can.
Dr. Jackson can.
Dr. Jackson can. I'm not surprised somehow, yes. Yeah. Uh-huh. Yeah, I've never tried. One time, I can't remember who won this, but Claire Yu, who was this student from South Korea, I still keep in touch with, 5 majors, including a self-designed biophysics major, got her PhD in developmental neuroscience at Johns Hopkins, then got an MD at Columbia, now then became an assistant professor of medicine at Rutgers, and is now going to the Mayo Clinic. Anyway, Claire, she and Dr. Trees got into a contest of writing H-bars, and so I think Dr. Trees won because, Claire's going, right, and Dr. Trees goes, H, 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 and then he just goes like that. Yeah, so, yeah. And then also at PH Cubed once, we were drawing numbers to win some prize, whoever got the highest number won. And Claire drew out a slip of paper that looked like that, and she goes, I got infinity, and well, of course she got 8 and she had it sideways. We decided to give it to her because, good, very good, okay. We handed her that. And then, one time, I never get distracted, and then one time, I was talking about why when I was in grad school living at the Chicago Theological Seminary, where I was in fact studying physics and astronomy, not theology, but still I lived there. We had a common kitchen where everybody could cook. And let's see, 3 stories. One, the kitchen manager told me about how the year before I came, they had a student from a country where men never cooked anything. That was a woman's job. And so, for the first time in his life, he had to cook. He had this raw chicken. He's looking around, how do I cook this? Never used a stove before. Solution. Put it on the burner and turn on the flame. This was not the right solution. The kitchen manager was really annoyed by this, apparently, he told me. Thing number 2 is that there was a group of Korean students there who were there for, studying for seminary. And I kept hearing my name all the time. Pop, 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 pop. Some of you already know what's coming here. And then they explained to me, and Claire was in an audience I was telling this to, she bends over, she just doubles over laughing because she knows what's coming. The Korean students patiently explained to me that bap means cooked rice basically in Korean. And so they were saying rice, 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 not pop, 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 pop. It's like, because I'd like turn to them and they were like ignoring me. I'm like, you're calling my name, why do you keep ignoring me? And then they laughed and explained it. So, and then the third thing is, I'm a hero, because one day I walk into the building and boy, it just smells so much like gas. And that's because somebody had left the burner on without the flame on. And so I went in and opened all the windows, and fortunately no sparks happened, because that would have blown. So now, was that the right thing to do? No, the right thing to do was call the fire department. But I don't know, I did that anyway. And so, yeah, those are my, right now I can think of, oh yeah, and then there's the time when we went up to the roof, because I had discovered and then there's this trap door, and there's Chicago Theological Seminary had this big tower, like 200 feet tall, and you go through this trap door, and there's like, the roof is like maybe this wide, and you could walk across the top of the roof, it's sloping roof and then a, top like it. You could walk across it if you wanted, and get into the tower. So I go up there with my friends John Krug and Alexander Arguelles, who you can find on YouTube now because he's a polyglot, and so he makes all these videos about languages and stuff like that. I go up there, because I had actually never opened the trapdoor. We opened it, and my response is, we'll look out, this will be fine. And John's response is, yes, we'll look out, this will be fine. Alex's response is, I'm going to walk across. And he's like, there's no constraints here. He could have fallen. And I let out a stream of curse words because I could not help myself. Because I'm like, I led you to this. If you fall off of this, I will never be able to live with myself that I showed you this, even though, yes, it was your choice. And so my buddy John still likes to recall the time, remember when you and I and Alexander went out there, and I've never heard you cuss like that in my life. So there's my 4 Chicago Theological Seminary stories. Back to our story here, because I'm laser focused on making progress in our learning here. Let's see. So let's apply this to escape speed and orbital energy. Escape speed and orbital energy. So, air friction, but imagine there's no air friction. You throw a ball. The faster you throw it, the higher it rises. If you can throw it fast enough, it would fly away from Earth, never to return, because never would it lose all of its kinetic energy. And so the minimum speed that it would need to fly away and never return, anybody know what that's called? Starts with an E. The escape speed, or the escape velocity. So better is the escape speed, right? Because we physicists are like, there's a difference between speed and velocity. Velocity is a vector. Speed is the magnitude of velocity. And then what do we say? Oh, the escape velocity. No, it's a speed! What's the matter with us? Anyway, the escape speed, that's why I was careful to say escape speed, but you'll hear me go escape velocity too. Because even physicists get sloppy and use them synonymously sometimes. But you should always be like, whenever you do it, right? So if I do it, you should raise your hand and say, speed, Dr. Hahn. So, all right, escape speed and orbital energy. If a particle is to have just enough energy to escape to infinity and beyond. escape to infinity after starting a distance r from the center, from the force center, I'll say, from the force center, then we'll have v goes to 0 as r goes to infinity. And since we've made this definition, I mean, you still get the same ultimate result here, but just a little more complicated if we can immediately say u was 0 at infinity. And since we've defined u goes to 0 as r goes to infinity, we have E equals k plus u equals 0 plus 0 as r goes to infinity. But wait a minute, energy is conserved, so if it goes to 0 as r approaches to infinity, it was always 0 to begin with, right? Whatever the particle's energy is, that's its energy no matter where it is. So, since energy is conserved, this means E is 0 for this particle in this situation. Since E is constant, it's not just going to 0 as r goes to infinity. E is just plain equal to 0 everywhere, no matter where the particle is. In other words, its kinetic energy is always equal and opposite to its potential energy in this situation. So if we want to find out what the escape speed is, we say E is 0 under that circumstance, but E is half mv squared minus g over r. Well, the little m's cancel. Doesn't matter what the mass of the particle is. All that matters is how fast it's going and where it started from. We're finding the escape speed as a function of where you're starting from. And so this says, 1/2 m, well, what did I say? 1/2 v escape squared is equal to gm over r. Or in other words, that the escape speed, the escape speed is just the square root of 2 big G big M over R. Voila, another very box-worthy equation. Notice it's a function of R. It's a function of where you're located, what the escape speed is at that point. It's a function of how far you are from the origin. But also notice that if a particle has the escape speed, it has the escape speed at every radius. As it moves further away, it's slowing down, but at that radius, it always has the escape speed for that radius. It's just a permanent property of the particle that wherever it is, it's at the local value of the escape speed that it's moving. If it's at any point moving the escape speed, it's always moving the escape speed, which is changing, but that's fine, because the further away you are, the smaller the escape speed is. Does that make sense? So it's always locked in at whatever the escape speed is. Doesn't mean it's moving at a constant speed. It's always moving with the escape speed, which is ever changing as its distance from the origin changes. Okay? So that's the borderline case. It's moving at escape speed with 0 energy. What if it was moving faster than the escape speed? Will it still fly away forever? will, but now, even at infinity, so to speak, right? This is really in the limit type of thing, but even at infinity, it's still moving in that case. It has enough kinetic energy, more than enough kinetic energy to just barely escape to infinity. What happens now is it's still moving once it gets to infinity, or really what we should say is that the speed approaches some finite value greater than 0 as r goes to infinity in that situation. So if v is greater than 0 as r approaches infinity, then the particle has more than enough energy to escape to infinity. And that's when it can go beyond. Sort of, not really, but. Has more than enough energy to escape to infinity. It is Buzz Lightyear. So this implies E is greater than 0. Its kinetic energy is greater than its potential energy. This, again, is assuming U is 0 at infinity. We're making that definition that U is 0 at infinity. Otherwise, we'd have to shift everything appropriately. So in other words, burn this into your brain. Positive energy orbits are unbound or open. They never come back. Unbound, also known as open, because there'll be a hyperbola, that conic section, instead of an ellipse, so they don't close back on themselves. You've probably heard of, y'all remember Oumuamua? So there's Oumuamua, there's another more recently discovered one, it's still in the solar system. How do we know that those are envoys from other star systems? Because when you add their kinetic energy to their potential energy at their distance from the sun, it's positive. They're moving faster than escape speed. And so they'll never come back. Long period comets will be on these very, very long elliptical orbits, but these are on hyperbolic orbits, and that's how we know that they're from another star system, basically, which is pretty cool. And again, it's understood that this is because we're setting U equals 0 to infinity. If we set it to something else, everything would get shifted. If the energy is greater than some constant, it's unbound, something like that. You know. If, on the other hand, the particle has insufficient energy to escape to infinity, so it's Buzz Lightyear. You really shouldn't have been drinking before he tried to launch himself. It is Buzz Lightyear. Then, in this case, what we'll find is that, what am I going to say? That the orbit is an ellipse, i.e., it is closed. So it's a closed orbit. Or we would also say a bound because it never gets further than a certain distance from the sun. It has some aphelion distance, and it never gets beyond that. And so, once again, in big, giant, flashing neon letters that you burn into your brain, we say negative energy orbits are bound or closed, which I kind of just said, but still just for symmetry and balance. I'll write that to be symmetry and balance with this one. Negative energy orbits are bound or closed. So it's really quite simple to tell whether an orbit is open or closed or right on the border. Is it moving faster than the escape speed or not? Tells you everything you need to know. It's moving faster than the escape speed. It's on a hyperbolic orbit. So I'll put that too. Hyperbolic. That's a hyperbolic orbit. Whereas, what kind of orbit is this? It's an elliptical orbit. Now, it's impossible for this to be really true because the energy can't be really truly zero, right? It can't be 0.0000005 trillion years later, 0.000 a couple years later, 0, 0, 0, right? It's got to be a little positive or a little negative. But that limiting hypothetical case that nothing could ever actually perfectly create, what kind of orbit would that be? It would be the other conic section. Not ellipse, not hyperbola, but a different bola. Parabola, yeah. It would be a parabola. E equals 0 would be a parabola. Parabolic orbit. Again, that's really just a hypothetical. It's not really truly on a parabolic orbit, but it can be so close that you might as well be kind of thing. Basically, as you get close to energy zero, the ellipse, the parabola, and the hyperbola would be so close to one another, you'd have to be way far away before you'd start to see them deviating from one another. That's what it comes down to.
What would that orbit look like? Just kind of
So a parabola is, one way to define a parabola is you have what's called the directrix, and then you've got the focus, right? And a parabola is a parabola. It would look like, it would plot like a parabola. And with a parabola, you can make this geometric definition where those two distances are equal to one another for every point on the parabola in that case. So in other words, this is halfway between the focus and the directrix. And as you move along the parabola, those two distances stay equal to one another. And it looks like a parabola, a good old parabola, y equals x squared, or that kind of thing. So it's literally a parabola. It's the same kind of parabola you know and love. The last thing we'll do is take a field trip in here. Too bad, you don't get to see this. Well, you can look at the book. Come on over just for fun here. Let's look at some high sections. These here were maybe before I even came here. Later you'll see them so those were the conic sections. What do you think?
Amazing.
Was it the most amazing thing you've ever seen?
That was
It was
crazy.
It
insane.
was. Oh my God, I feel sorry for somebody who's never been able to like see that. Oh well, all right.